accuracy class in much more details. Okay. First factors to be considered during the time you want to select the current transformer will be the accuracy class. So it's actually choose based on the precision level, how accurate it will be. So to find the percentage ratios areas, here is the formula where we have a ratios of magnetizing current divided with the secondary current flow multiplied with 100%. So from here you can see if we are able to have this, i.e. the magnetizing current as low as possible, then the areas from the current transfer will be lower. Alright, that's why I'm always mentioning the magnetizing current has to keep as low as possible. Zero, which means zero error, right? So for many current transformers, the acceptable range in terms of accuracy will be within this range, plus minus 10% up to plus minus 15%. So what if I apply the current transfer for distance predictions as well as the differentials relay? So this time I have to have a much more titles in terms of accuracy percentage here. So it will be tightened to plus minus 3% to plus minus 5%. So I have one table here actually showing the standard precision class of current transformer, and it has been divided in according to the applications. So we have class from 0.1 up to 1 here. So this magnitude is actually showing you what is the percentage area we can obtain or generate from the current transfer, like 0.1 with plus minus 0.1, 1 with plus minus 1 here. So whenever you see this class without the alphabet P, right, without alphabet P, we know that these kinds of current transfer is used for metering purpose to get current measurements on it. So in the event, if you notice that it's being labeled with P, P indicates use for protection purpose. So these two are the protection class of current transformer. So we have 5P, 10P. 5 and 10P is actually giving us the composite areas, right? In which it can give you the percentage error of plus minus 1%, 10 give you plus minus 3%. Right? That is in terms of accuracy class, how you can select based on the applications. All right, so now let's see this example. This is actually same as the previous example. We want to see how to find the current transfer error for these specific situations. Right? It's actually continue for these examples. Alright, so in the event, if you want to find the percentage ratios areas for the current transfer we are using in the previous example, we know we have to apply these formulas, right? Which is the ratios of magnetizing currents with the secondary current. Then multiply with percentage to get the percentage values. So for the secondary currents, we just now already found, right? Whenever we are measuring the 10 kilo amp, the equivalent secondary current value will be 100 amps. All right. So what would be the IE value, the magnetizing current value? This value can actually abstract from the magnetization curve here. So just now we have calculated that the secondary voltage is 60 volts, right? We know that it's actually at this horizontal line. So, and we have to refer the second curve here because we are referring the current with these ratios 500 to 5. So find the intersections in x-axis would be the magnetizing current. So in these situations, we will have the magnetizing currents here, IE as 0.1 ampere. So just substitute into these equations here, you can find what is the percentage ratios areas for this current transformer. So it will be at the value at 0.1%, right? So it's very easy. Just memorize this formula. Okay, you can try out the questions we have in the tutorial. So that is based on the accuracy level. So what is the another factors I have to consider during the time if I want to select the current transfer would be what would be the secondary current rated value? We have 1 amp and 5 amp, right? So in the event, if you are expecting to have a long distance connecting from the relay as well as the current transfer, so this indicates we have a situations where the cable resistance is very high. So with this scenario, we usually will prefer to use the current transfer with the secondary current rated at 1 amp instead. But then for indoor applications, so the distance between the relay current transfer is not so high right now. So we can use much higher ratings like 5 amp in such a case. So, but for this 1 amps of secondary currents rated current transformers, right, it should not apply to the system that expecting to measure high currents value. Why? This is because if I want to measure this high currents value with this low ratings of the secondary current transformer, I will need to increase the numbers of winding turn at the secondary side. So it's like a a multiplication factors. Higher number turns here, I can measure much higher current value. So if you are in the event of applying a low ratings current transfer for these situations, you will actually have a problems like having a very bulky current transfer because the numbers of turns is much more higher. The size has increased, and of course, the cost will be increased as well whenever you increase the numbers of turn at the secondary side. Okay, so this is based on the rated secondary current value for the current transformer. We have another factors here in terms of accuracy limit factors, ALF. And this is only applicable for protection class of current transformer. So we know that whenever current transfer used for protection purpose is expected to measure a large fault current value, all right, in which we have to comply with this composite area requirements for this current transformer. So what is actually the composite area? So let's look down here by looking into this dialog box here. Composite area is actually in terms of RMS value. What is the difference between the primary current at that instance comparing with the incident current multiplied with the turns ratio, which is this models here under steady state conditions. So for this ALF values, right, it can be obtained by using these expressions where we are trying to calculate by dividing the maximum currents expected to be measured, which is obtained whenever we are having a three-phase board being short circuit together, which is a three-phase board following a current triangle locations, divided with what is the rated currents at the primary side during normal conditions. Okay, only protection class of current transfer is being provided with ALF, the accuracy limit factors. All right, so let's check out these examples here. How actually we can read the spec of the current transfer, which is specified by REC standards. Let's say it's being written in this way: 50 watt ampere, 5P10. From P, you know this is for protection class. So watt ampere here, so from this unit, you can tell this is actually the burdens rating. Okay, 5P10s. All right, so what is actually 5 here? 5 is actually indicate what is the accuracy in terms of percentage. So it will give us 5% in terms of accuracy if it's able to comply the composite errors that's being specified at 10, which is 10 times of the rated primary currents under fault conditions. So if let's say the primary current exceeds this limit here, 10 times of the rated current flow through the primary side, the reading at the secondary side will actually become distorted. So the protections will not be guaranteed. So that's how we decode the spec of this protection class of current transformer. Okay, so we have multiple factors again to be considered. The next one we have is a short time current rating. So this is same as what we have learned for circuit breakers. Short time will be the durations where this current transfer is able to withstand the maximum fault current value for these specific durations of time without being damaged. So usually it will be specified in the units of cycle like 1 to 3 cycle time. All right, so the magnitudes of the currents that be withstand by the current transfers here is actually depending on this factor, which is what is the current value, of course. So what is the fault current value for these durations of time? How long would be? It will be stay within the system. What is the acceleration peak value? Remember, only occurs at the first cycles of the current waveform. We have to treat this as well as the maximum current can be withstand by this current transformer, as well as what would be the transients for that at the instance we have faults occurs. All right, so that is based on the short times rating for the current transformer. So we have two more factors here. This is what we have learned in terms of knee pole voltage as well as burdens ratings. So of course, different relays or different instruments will give us different burdens, right? Like ammeters, it will give you the burdens approximate for 5 watt ampere for the 5 amp current transformers. You usually want to lower down this burdens value, then only we are able to get the correct current measurements. In terms of knee pole voltage, again, based on the burdens here, what would be the voltage here at the secondary side? You have to ensure is always below the knee pole voltage, right? For different components placed at the secondary side of the current transfer so that it will not turn into saturation mode. So here are all the factors that will affect the selections of the current transformer. Okay, so I think it's very long. We have one more topic. All right, I try to finish it as soon as possible. So we are at the last topics right now. What is the possible issue might be faced, right? If we are applying the current transformer for measurements. Okay, the first problem here is actually what we have learned just now, where it states that the secondary side of the current transfer should not left open circuit. All right, if you still remember. So in the event if we have a secondary side of the current transfer become open circuit, what is happening is that if you still remember, there will be voltage being induced at the secondary side. So this voltage induced, or I should say the EMF induced at the secondary winding, will actually cause the current flowing through the impedance, which is the burdens right now. And at the same time, we have the magnetizing current flow. And this magnetizing is due to the difference between the primary and secondary ampere turns, right? The area is actually come from here. So what happens here is open circuit. There will be no secondary ampere turns being generated as the opposing force for this primary winding turns, right? So which means there's no opposing force to the primary side. So with such a case, the whole primary ampere turns here will be used to generate the flux, which means that we have high flux is being generated. So whenever we have high flux, what happens? It will turn the core turn into saturation mode. All right, so to further explain this, let's move to the next slide here to see some waveform. So you will notice that there will be highest rates of flux change every time in the core whenever the primary currents reach to zero. So if you refer to these figures here, this is the voltage induced like this in this pattern. This is the primary current flow, right? Under the situations if at open circuit conditions at the secondary side. And this is the flux being generated within the core. So you'll notice that whenever current reach to zero, we have maximum high voltage is being induced due to high flux is being generated at the core. So which means that the core will turn into saturation mode every half cycles of the current waveform. So with such a case, core turn into saturation. What happened if you the wrong reading correct? So this situation is still okay if we are using the current transformers with secondary currents rated at 5 amps, right? So under these situations, the voltage induced right at the secondary side is not still harmful for this current transformer, which is used for measuring purpose. But if we are using a protection class of current transformer, let's say with these ratios here, so you convert 2000 to 1200 times smaller, and these current transformers also being configured with large core sections expected to store much higher flux value. So if we are using this current transformer, So the peak voltage generated will be much more larger, which could reach multiple values of kilowatts. So which means that the insulations of the current transfer will become damaged. So with such a case, it will give the dangerous situation to the operator. So as always being mentioned, the solution to this, never ever let secondary side of the current transformer become open circuit. We have to terminate it with a low resistance value or by using the switch, right? So that is the problem we have to focus on in order to ensure the current transfer give us the correct measurement as well as doesn't being damaged because you open circuit it, okay? And we have another problems as well coming from the current transfer, which is due to DC saturation. So whenever we have short circuit occur within the power system, if you measure the fault currents, right, you will notice that the first cycles of the current waveform is actually accompanied with the DC component, which is occur in transient manner, which means that it will slowly decay to zero once it's reached the steady state conditions. And this DC component can actually cause the current transfer called turn into saturation mode. And not only this, whenever we're energizing the large utility transformer, which means that you power up a transformer, it will also give us the DC saturation scenario as well. So under this situation, right, the current transfer doesn't able to give you the right measurements against. So let's check out these figures here. So what happens if we try to measure the current value, right? Under the decisions, we have DC saturation. So let's say this is a primary current that need to be measured and we have 1:1 ratio. The dotted line is actually the secondary current. You will notice that the current is actually dropped, right? Close to zero for certain conditions here. So which means that this DC saturation is causing wrong measurements from the current, right? Current transfers right now. So now under these situations, right, you will notice that the flux induced due to the DC component is actually rise with this value, which is approximate to the ratios of reactance to the resistance to that, or due to the power factors of the load right now, it will actually cause the current transfer called turn into saturation mode. So to further understand this, let's check out these figures here. Okay, let's say we want to plot the flux with respect with time. And this is the maximum limit where if exceed this line here, it will enter into saturation mode. So under normal conditions, this is the flux generated from the core of the current transformers. So what happens if we have faults occurs and then it comes with DC offset, right? It will cause this flux here, how to say, increase right now due to the DC component. So with such a case, this dotted line here is the possible flux generated due to the DC component, in which right now is higher than the saturation levels right now. So that's how it's under into saturation mode. Right, so that is what we also need to be considered as well. We need to know what would be the magnitudes of the fault current that come with these DC components here, in which it will not cause the flux generated here higher than the saturation mode, else the current transformer unable to work properly. So this is basically the another problems we could found whenever we use current transfer for current measurements. So with such, we are reaching the end of this class here for chapter 3. We have talked about voltage transfer, most of current